Goodness gracious alive. Goodness gracious alive. We're running around like chickens with their heads cut off over here. Welcome to the Oscope Wizard. I'm Gabe, the Oscope Wizard. And it is Band Shirt Tuesday. Although there is a slight change in the plan for Band Shirt Tuesday. Because I've honestly, I've worn all my band shirts. And I've worn a couple of them twice because I really love them. And I love band shirts. But today, there is a slight change, a slight variation on nerd shirts. This is a video game shirt. I got a couple of video game shirts to go along with my band shirts. You got to mix it up a little bit. But this, does anyone recognize the symbol here? Anybody? Anybody? It's a pretty famous video game. Eventually, the chat will catch up. I can see the computer's lagging behind. I don't know. It feels like it's lagging behind an hour, but it's just a couple of seconds. So I'm not going to spoil the surprise. Somebody in chat will probably shout out the name of the video game that this shirt comes from. It's my favorite video game, perhaps of all time. Well, at least one of them. Otherwise, though, it is Tuesday, and we are continuing our journey to build Dungeons and Dragons was one of the guesses from the chat. No, you are incorrect. But I'm going to tell you because I love this video game. This is the Triforce of Power, from Zelda. And my favorite video game is Zelda: A Link to the Past. I really love that video game. It's a great video game. Anyway, back to the show. The actual Oscope Wizard. We are like elbows deep in our journey. We are trying to build an IRL subtitle necklace that will do voice recognition and speech to text in real time, or as close to real time as we could get. The chat had no clue about the video game. Oh my goodness, my chat, you're so good at math and yet so bad at video games. I guess if we had to choose a skill, being better at math than video games is probably a good trade. Here's the show today, though. We've had to punt a little bit. We've had to change tack, or change our mind, veer. Our project has taken us down a twisty, windy road, and two roads diverged in a wood. We are taking the one less traveled, or the one maybe perhaps more traveled, actually, ironically. We're changing our Raspberry Pi Zero. So we had a Raspberry Pi Zero, and it didn't work that well for real-time speech recognition. In the background, I had a Raspberry Pi 4. I've never worked with a Raspberry Pi 4, so this is actually something new for me. I don't know if it's something new for you. I went to the store. I bought a Raspberry Pi 4. I unboxed it. I got the fancy Raspberry Pi 4 power supply, which is USB-C. So that's a little bit different. Normally, they are micro USB. So here's a micro USB. Which is a little bit different than the Raspberry Pi. The Raspberry Pi uses a Type-C connector, which is this guy. Eventually, hopefully, all the devices in the world will switch to Type-C because Type-C you can plug in either way. There's no keying. So either way, and the connector is designed as such to make sure you always plugged it in the right way. I love it. It also allows for more current. So I think that is one of the big things that the Raspberry Pi 4 is utilizing, is you can get higher voltage. So normal USB is locked into 5 volts. Type-C USB lets you kick it up to, I think, 20 volts. 20 volts. You can do 100 watts. So 100 watt, it can move a lot of amps. It can move a lot of amps, much more than USB 2. USB, this connector was really limited to 1 amp and 5 volts. 5 times 1 is 5. I can do that math. So 5 watts. And some of the connectors pushed it. As we all know, if we got tablets, all of those power adapters were 2 amps. So 5 times 2 is 10. But now USB Type C, we're talking about 100 watts, 100 watts. So way, way more wattage. This is going to hopefully let the Raspberry Pi kind of unleash its power. We can use more power on the processor. It can run faster, run hotter, and maybe do things a little more quickly. With that in mind, let's figure out where we were last time and where we want to go. And also to make us, I see I've already gone 5 or 6 minutes without hitting my timer. Timer's on. We're back in business. We're back on time. When we were using the Raspberry Pi Zero, we like it because it is super low current, low power. It sips current and does a lot for very little current, but it turns out speech to text is a pretty process intensive operation, if you will. You can either try to do it offline like we were doing with PocketSphinx, if you remember, and that wasn't going so well because PocketSphinx is super slow. It was very effective at collecting the speech and sending it to the Google Cloud. The Google Cloud, immense computing capabilities. Every time I think about that, I always think about the genie from Aladdin. And he's like, enormous, what was it? Enormous power, itty bitty little space. So the cloud is like this enormously powerful thing, but we have this small thread between us and this cloud. Through the Raspberry Pi, it sends the stuff out to the internet. The cloud decodes the text into, or the speech into text for us, and then sends it back to the Raspberry Pi. I did not want to have to be tethered to the internet the whole time that I'm using this device, though. So we need to figure out if we can get offline working on my Raspberry Pi 4. If the offline works fast enough to be acceptable, not accessible, acceptable, I want it to be, it has to be fast. And then here's our Neopixel. So I got the LEDs back out. We want to draw text on this LED strip. Hopefully, that's what we're going to go for. And then we also need to figure out, so I have a battery in the mix because it's going to be really hard. This battery, I swanny. I mean, look at this. I moved it. It doesn't even have a gyroscope on it. How's it turning on all the time? I figured out if you double press this tiny little button, it turns off. But I mean, look, like you just bump it and it's like, I want to turn on. What I don't know what's tipping it off, but it turns on at the drop of a hat. Literally the drop of a hat. So we need to make some more current measurements, though, to determine how long our battery's going to last. And we made current measurements on our Raspberry Pi Zero. You can see the Pi Zero, 220 milliamps. That is hardly any milliamps at all. The Neopixel was the big behemoth, up to almost an amp, 760 milliamps when it's fully illuminated. And then the audio board was nothing, 30 milliamps. These little microphones aren't drawing much current, and we're not really sending audio out. We're just collecting audio with the microphones. Where were we before? Let's go over to my browser. This is where we were before. We were trying to make PocketSphinx work on a Raspberry Pi, and we did make it work. And we even got, let's see, we got the Python speech recognition engine going, which was really cool because this guy let me use a bunch of different things. This is how I was able to determine that PocketSphinx was way slower than, so here's the PocketSphinx in the Python library, and here is the Google API in the Python library. That's how I was able to determine that PocketSphinx was so much slower than Google. So PocketSphinx working offline was slower than sending stuff from the techno layer out to the mysterious cloud, back from the mysterious cloud to the techno layer, onto my screen. PocketSphinx still could not keep up. So is it still so slow if we do that on the Raspberry Pi 4? I'm curious. I am curious if it will work any better on the Raspberry Pi 4. So let's start there. So let's start where we finished last time. We are on the Raspberry Pi 4. This is the Raspberry Pi 4. A terminal window is opened up. Let's take a look. We have a speech recognition example right here. Let's just take a real quick look at it. We can open it up with Nano. And we can see, look, we imported speech recognition. We turn on the microphone, which is super easy. We tell it, wait no more than 10 seconds. We did have this at 10,000 seconds and figured out that that was a little bit long of a timeout. Then we send it to Sphinx, so PocketSphinx. We do it with PocketSphinx. And next, we send it to Google Speech Recognition. So, ta-da, ta-da. I wonder if I can. So it gets, I just want to add a real quick change. I want to say print. So I want to know when this thing has actually collected data. So I'm going to say print processing audio. And that, when we run this little example, I just want to know that it's done collecting audio and it's processing it. So when it is finished collecting this audio, tell me it's processing, and then we can count how long it will take to. Actually, we could build a timer in there. I'm not going to go to that level. We won't do that because I don't have to do I don't know how to do that off the top of my head, and I would only embarrass myself. So let's run this. Python 3. It's got to open up the microphone. We are saying things. What is PocketSphinx going to think we said? What is Google going to think we said? I like the fact that it has a pretty far field microphone. There we go. We're processing audio. We'll see if it got any of that processed. But as we wait, the seconds drift by. So even the Raspberry Pi 4, it's a little fast. It's faster than the Raspberry Pi Zero with the PocketSphinx. But PocketSphinx thinks we said, home, we're saying things like these pockets, things going to think we said, what is the one thing he said I've offended as a pretty far to mine? Do you English, bro? Do you English, bro? Does PocketSphinx English, bro? And then Google will be pretty good. What does it think we said? We are saying things. What is PocketSphinx going to think we said? What is Google going to think we said? I think the fact that it has a pretty far field. Man, Google is crazy how good it is at speech recognition. It's bananas. My microphone was kind of bumping into my throat. My Adam's apple is jumping around. I'm so excited about speech recognition. It's crazy. This tells me that PocketSphinx is just a non-starter for anything real time. It's just not going to work. It's just not fast enough to get speech collected, detected, translated into text, and then out. It is too slow of a mechanism. So that brings me back to the beginning. I feel like we're in the circular path on this particular project, because this is where we began. Offline speech recognition on a Raspberry Pi 4 with a respeaker. This was the original document that I showed on the first show about this whole project. And we decided that this project uses Mozilla's Deepspeech ASR, which is what the cool kids call automatic speech recognition. And we decided we couldn't use this because we did not have a Raspberry Pi 4. It says you need a Raspberry Pi 4. And when we tried to install this on our Raspberry Pi Zero, it did not work. Now we have a Raspberry Pi 4. And guess what I did? Hint. I have just highlighted the command that I ran, which is pip3 for Python 3, install Deepspeech. So now we have Deepspeech, this Mozilla project that I have seen. I have seen it called out a number of times. a number of different places for a really fast speech recognition. And in fact, this guy's like, it is faster than real time, which we decided was beyond the scope of the project because we do not do time travel here. Not in this project, maybe in a future project. It gave me hope, though, that on Raspberry Pi 4, this might be fast enough to actually decode speech. So there's an example here. Here it is. We're going to try to run this example. I think I actually have this example ready to roll. If I go to, I think I got to go to Deepspeech. I think I have Deepspeech. Is that it? Yes, there we are. So here is my model and my scorer. Oh, well, wait a second. Let's go over to the terminal so we can follow along. Here's the terminal. Here's my model and my scorer. And now I'm going to go into the examples and we're going to take a look at what is happening in this example real quick so that we can understand what we're doing. We're going to try to understand what we're doing. We are doing the mic badge streaming example. First, let's take a look at the code. Mic badge streaming. See, raw audio from the microphone, data is received in a separate thread. So, oh, this is doing threadings and it's put in a buffer, which is pretty cool. And then that buffer is going to be read out and processed. There's one channel, which is perfect because microphones are generally mono. I only have the one mouth. I only need the one audio channel. Am I still on this browser? What in the sweet mercy? I haven't gone over here. There we go. How did I turn browser back on? That was a mistake. Sorry about that. Here is the audio, or here is the code for this microphone streaming example. You can see it uses Deepspeech right there. That's the big library that we're using from Mozilla. And what's kind of crazy is I think of Mozilla as a internet browser company, but really it's an open source software company. Which is kind of cool. So cranks up my stream right here. Finds the input device, which I suppose I can define. It might not support the native processing rate, but I think our microphone will support it. And it can do it from a WAV file, but we don't want to do it from the WAV file. We want to do it from the voice, from the microphone directly in VAD. Filter and segment audio with voice activity detection, which this is really cool because built-in voice detection in this program makes it so that I can keep talking and it'll keep collecting different chunks of my audio. So let's close this. Let's just real quick take a look at the README. Just making sure here. Yep. So this is going to use Deepspeech voice activity detection, and it says it's a fairly simple example demonstrating the Deepspeech streaming API, which I am going to eventually, hopefully, manipulate to get the text out of so that I can send it to my LEDs. I want to send it to my LEDs. So this is, I don't think I have to actually define a device because I only have the one device. I only have one microphone connected to my Raspberry Pi. I think that's it. I think I need to tell it the VAD aggressiveness, which we will set to 3, the most aggressive. Okay, so let's back out. So we're back at our directory that has the model for our language, for the Deepspeech model. And I think I can just do this Python 3 / Deepspeech / deeps. Will it not do it? Hold on. There we go. Deepspeech examples mic bad streaming, mic bad streaming.py. Uh-oh. Let me pull it back over so I can see it. I think I want it to be -v3. I don't think I need to do anything else. So let's see if this will actually decode my speech into text. What will happen if I just hit enter right here? Oh, I need to tell it the model. Oh my goodness, I forgot to tell it the model. Okay, let's see. Let's do this. I'm going to copy the example from the web page. I don't think I need this. I don't think I need these. I don't think I need -t try, and I don't think I need -lm. All right, so this is pointed to the model. Is that right? No. -m. -m. Let's do this. Okay, my model is right here. Deep speech dash 0 dot. Let's get it. 8. Uh-oh, what did I do? Oh, there we go. I got 2 8s. Kind of getting ahead of the, there we go. 2 dash models dot tfl ite. There we go. If I'm going to copy the nomenclature that was there before. Can't open file, no such file. Okay, I have definitely made a mistake somewhere. Okay, maybe I need to do this. I need to tell it that I need to make that executable. That model needs to be executable. Uh-oh. Oh, this had thrown it off. So this directory structure thing right here. How about this? Ooh, that's pretty promising. Oh, it's even got a spinny wheel to tell me that it's active. It's listening. Is it going to do anything? Oh, wow. Okay. It's saying things as promised. Some of that is not English. This looks like it looks like it's working. Do I have this incorrect? Well, maybe, wait, let me get closer to the microphone because it might not be hearing me. Let me get closer to the microphone. Can you hear me, microphone? Can you hear me? Are you hearing me? Microphone. Hello, microphone. Why am I talking to the microphone like it's a person? This is really hard to make work. Coding is tough. It seems stuck. It does seem stuck. I may have, oh, wait a second. Whoa. It's got a really long buffer there. Well, okay. So late is not English. This looks like it looks like it's working. Do I have this? Are you marry me microphone? Hello, microphone. It seems. Now it's working. Now it's on top of it. It does seem stuck. I think this will work. I think this will actually work, guys. I feel good about this. We're getting text to speech. It's pretty fast. What if I change the what if I change the aggressiveness of the voice detection to 0? What if we make it the least aggressive? What happens then? Now our voice detection is set to 0 aggressiveness. Does that improve or diminish our accuracy? Hello, voice detection. It is not detecting anything. Seems like 0 makes it not work. Okay. So 3 is like hyper aggressive. Oh my gosh. Hold on. I think I've got 5 minutes remaining.
5 minutes left. I was
There is but 5 minutes remaining. We did get voice detection working with deep speech, so I have high hopes that that will actually be a viable option. Before we go, though, there is a pretty big second part to our saga. Now that we have offline speech detection working reasonably quickly, and I think I can probably speed it up even faster. It's way faster than PocketSphinx. Way faster than PocketSphinx. When I was messing around with this, not on the camera, I did have it working a little bit more smoothly, I'll say. Let me start my 5-minute timer so I don't go too far over time. If I go back, though, to my setup, you'll notice I have these LEDs over here. So these are a pretty big component of what we're trying to do. And I haven't used them in a while. The last time we used them, all I did really was flash them on and off. And there was a lady named Caroline who built a project. And here is the article about the project that she built on Tom's Hardware. And she made these scrolling face masks out of this LED strip that I have, or my Neopixel strip that I have. And one of the things that I was struggling with was how it seems so simple. How do I get text onto that Neopixel? It's really easy to turn pixels on and off, change shapes, change colors, animate it. How do you get text onto it? And I was struggling with how to do this. And one of the things that Caroline did was post her code, which thankfully has scrolling text on it. So let's take a look at this scrolling text routine that she wrote, that I downloaded onto the Raspberry Pi, so we can figure out how to get text scrolling onto our Raspberry Pi. So we want the text to scroll across here from here, and we have it all wired up. We have D18 is my data line, and then I have the power and ground hooked up to the Raspberry Pi GPIO lines. And after we get all that working, we probably should measure the current again, because that's going to be, I anticipate, quite a bit different than it was on the Raspberry Pi Zero. Go back. Okay, we don't want to do, we're good on deep speech examples right now. I just want to clear that. Let's back up. Okay, get out of that directory. Scrolling text mask. Let's go to the scrolling text mask directory. And there is a test message. So let's open that up. Test message.py. Take a look at it. So I had to make some changes because I'm using a 256 pixel grid. We probably don't want it to say welcome to Tom's Hardware. Not that that's bad. I mean, I have read Tom's Hardware since I was in college. That was one of the first places that I could go to get motherboard reviews. I mean, I used to read Tom's Hardware like a religious text because I needed to know what motherboard to buy. That was a really big deal in college. Um, the AMD Athlon had just come out. You had to choose between the Athlon or the Pentium. It's a big deal, a big deal. But we'll put the O-Scope Wizard and maybe 9 exclamation points, 4 exclamation points. Let's see if we can get that out to the board. I need to tell it that I'm hooked up to D18, which I've done before, past projects. This is the magic though. So she's importing image draw, and image font. So they set a font to this 5x7 TrueType font. I'm not sure. I don't have that many fonts on this Raspberry Pi because I installed it with just the terminal, so not a GUI. But I could get more fonts onto it, and we can check out what they look like. Then she makes a grid of an image over here. So we make an image that is the text width plus display width plus display width plus display height, and then draws the image, and then takes that image and sends it out to the pixels. So slowly but surely writes that image out to the pixel, or to the Neopixel. And I just, man, my tiny mind was really struggling with how to make all of that work. And in fact, it looks like this text is drawn into the image PNG. I wonder if I took a look at that image PNG. I don't think I can open it up on this computer, but I suspect it's just like a dummy image here. So we will save it. All right, we'll stop it, and let's just run it really quickly and see if we can get, if the text does scroll across our Neopixel. So I'm going to run that thing that we just looked at, sudo python 3 test message.py. There we go. Look, the O-Scope Wizard with 4 exclamation points. It did work. It did work. So now, next steps. Let's measure some current and figure out how long our battery is going to last. And then let's figure out how to get the text from the Deepspeech engine out to our Neopixels using this really clever code written by Caroline. And I will link to her article on Tom's Hardware so that you can download the code if you want to as well. I don't know all the nerds in the world, but I'd love to meet them. So please share this with a nerd in your life. Join me on the next O-Scope Wizard on Baby Friday of this week, where we're going to make some measurements. We're going to write some code. We're going to nerd out together. I really appreciate it. I'll see you guys later. Bye.